Consider a random walker. At each time step, the walker can move either one step to the right or one step to the left, each with equal probability 1/2. We call this process a simple symmetric random walk. The first few steps of such a process could look something like this. This process has two properties that we're interested in here. First, at any time, the average position of the random walker is equal to its starting position. This is what's known as the martingale property. We also say that the process has unit speed because in each time step, the process moves just one step in space. If we scale space and time appropriately, this process has a continuous limit with the same two properties, which is the one-dimensional Brownian motion. Now in one dimension, this is the only continuous process with the martingale property that moves in some sense at unit speed. In two dimensions, however, there are infinitely many processes with these properties. The question that we want to ask is in two dimensions, how can we choose a martingale that is optimal in some sense? Let's consider two simple examples. First, suppose that a process moves in the disk and there is a penalty for spending time in the shaded outer region. We want to find a process that minimizes the average penalty. To do this, we draw a line through the center of the disk and we just perform a simple symmetric random walk as we saw before on this line. Again, this process has a continuous limit and you can see a sample path on the left of that continuous process and its radius on the right, where you can see that the process spends a lot of time close to the center of the domain and away from the area with the penalty. Now let's consider the opposite scenario, where there is a penalty for spending time in this central shaded region. To minimize our average penalty again, we want to construct a process that's always moving outwards, away from the center of the circle. To do this, draw a tangent to the current position, and to preserve the martingale property, move in either direction on this line with equal probability. Repeating this construction, we arrive at a process that lives on circles of increasing radius. This time, the continuous limit of this process has sample paths that look like the one shown on the left here, and the radius is actually a deterministic increasing function of time, the square root function that you can see here on the right. We can show that, more generally, for penalties that depend on the radius of the process, that an optimal continuous martingale is one that switches between the two types of behavior that we've just demonstrated. And you can see the sample path of such a process in this final picture here.